Hello and welcome to the fourth of the lectures in this week 5 of the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. So far this week, we have seen what fuzzy relations are, where they can arise, and a few different types of fuzzy relations. We have also seen how to compose fuzzy relations. We have seen here there are many possibilities and interpretations. We've also seen that from the similarity and compatibility relations, we can extract similarity and compatibility classes, and we have seen their utility or usefulness in the last lecture. It is our quest using these relations, special relations, we would like to unearth some interesting information about the elements of X itself. In this quest, we will continue, and we have seen that transitivity plays an important role if you would like to actually come up with some kind of a partition on the underlying set X. If you would like to group objects based on their similarity levels, then transitivity plays an important role. In this lecture, we will see how to infuse this transitivity to a given fuzzy relation. We will define what is a transitive closure of a fuzzy relation with respect to a T norm T, and we will also come up with a very simple algorithm to actually calculate or determine this transitive closure. We'll end with a few practical illustrations of what we have seen in the previous class, previous lecture, and also in this lecture. Let's begin with a quick recap of what similarity classes are. They are fuzzy relations which are reflexive, symmetric, and transitive. We know that because of the transitivity, if we consider the alpha cuts, if the fuzzy relation is min-transitive, then we can obtain partitions on the set X for different resolutions of alpha. Compatibility classes are like similarity classes, except that they do not have transitivity, and we found that this was a singular reason why we were not able to obtain partitions from the different alpha cuts. Instead, we were only obtaining overlapping compatibility classes. Of course, they were covering the set X but not partitioning it. We stopped with this question in the last lecture. Where do we get these compatibility relations from? Let's look at least two scenarios. First of them, let A denote a set of attributes and X a set of all people expressing their preferences on this set of attributes. You could think of the set of attributes as probably just a set of movies and people giving their preferences. Now, we may construct a fuzzy relation on X, binary fuzzy relation on X, which expresses the similarity between the preferences of the different people. Now, note that even in the example that we have given of ranking movies or giving preferences from a set of movies, we know that this is the kind of information that can be made use of to make recommendations. There was another interesting work done by Tamura and others way back in 1971, in which they took a set of portraits of members of some families and they wanted to capture the similarity in the appearances between any two photographs. Now, these similarities themselves cannot be generated automatically. That means human subjects were involved in it, and they were given pairs of them and asked to measure the similarity between these two pictures. This is how they had constructed the similarity relation R. It is clear now that it is way too much to expect this relation to be transitive also. Clearly, it is symmetric because it doesn't matter which way you are comparing a pair of photographs, but it is unlikely to be transitive, and especially min-transitive. However, what they wanted to do was, they wanted to make use of this relation and see whether the portraits could be grouped into families. Now, what gave them this confidence, or where were they basing this reason on? Is transitivity lurking here? Yes, definitely. They know that the parents, the father and mother, they may not look similar. However, their similarity perhaps is related through their offsprings. So this is how their similarity can be thought of as being transitive through their offsprings. So you see here, in these two scenarios that we have actually extracted relations which are fuzzy relations and which are unlikely to be transitive. However, they are symmetric and they could easily be made reflexive. For instance, like when we are talking about preferences, take two people who have given preferences on the same set of attributes. If x and y are same, then the preference level matches completely and you could give a similarity value of 1. Well, let's move on. Let's look at what is transitive closure. Before that, the concept of transitivity itself is related to some kind of composition. Let's look at what is T-transitive. So we said that a relation, fuzzy relation, is T-transitive if this inequality holds. But now look at the sub-T composition. So when R is on x cross y and S is on y cross z, we compose R and S like this. If instead of taking S to be from y cross z, if you instead take S to be R itself, what we have is essentially this composition coming in here. So from these two, we could also define transitivity in an alternate but equivalent way. We say R is T-transitive if and only if R circle TR is less than or equal to R. So you see here, the transitivity of a fuzzy relation with respect to T is in fact related to the sub T or max T composition. Let's for the moment assume that X is only finite and so it's easy to take supremum to be maximum. Let's define what we mean by transitive closure. For that, let us consider a relation, fuzzy relation R on X and T at T0. We say the fuzzy relation denoted by RT star is the T-transitive closure of R if RT star is the smallest T-transitive fuzzy relation containing R. Now let's decode this a bit. So what do we expect RT star to be? First of all, RT star should be T-transitive. And if S is some relation which contains R and is also T-transitive, then we expect that S is bigger than RT star 2. So RT star is T-transitive and the smallest such transitive relation, T-transitive relation containing R. Well, this is the definition. But how do we actually find the transitive closure of a fuzzy relation R with respect to a T non T? Fortunately, we have a result, and it is not only a result, it's also an algorithm. Let's be given a fuzzy relation R and a T non T. By this notation R superscript 1, we denote the relation R itself. We recursively define what is R superscript n. It is nothing but R composed with R power n minus 1 or R n minus 1 with respect to the sub T composition. Look, T is fixed here, sub T composition. So R2 is nothing but R circle R, R3 is R circle R2, which is R circle R composed with R composed with R. Now, what is the transitive closure of an R with respect to a T? It can simply be written as the union of all such recursive compositions. That means it is R union R2 union R3, so on and so forth. Now, the formula looks very simple, but it really does the job for us. That means RT star is T-transitive and in fact it is the smallest T-transitive relation containing R. Let's look into the proof of this. What we want is, what we are given is RT star is defined like this. We need to prove two things. Firstly, show that RT star is in fact T-transitive. What does this mean? This means in terms of the composition, RT star circle T, RT star is in fact less than or equal to RT star. Let's start with this. Let's start with the LHS. What is RT star composed sub T composition with RT star? It's nothing but union n is equal to 1 to infinity Rn sub T composition with union, let's use a different index here, Rn. Now what is this? You might recall from the previous lecture that if we are discussing sub T composition with relations appropriately defined and J being the index set, we see that P circle T union Qj is nothing but union of P circle T Qj. That means we are able to pull out the union operation, which is essentially the max operation here, outside of this bracket. This once again follows because T and max distribute over each other. As I said, we will have an entire lecture discussing different functional equations. At that time, we will also visit distributivity of fuzzy logic connectives over one another. So using this property, we could pull out both of them and write this as union n is equal to 1 to infinity, union m is equal to 1 to infinity, R n circle T R n. But now this could also be written as union n comma n equal to 1 to infinity. Note that by the recursive definition that we have here, this is nothing but R power n plus n. Now as n and m vary from 1 to infinity, what we get is union k is equal to 2 to infinity R power k. Because n and m they start from 1, which means they start with 2, so k is equal to 2 to infinity. Now we know that this is definitely less than or equal to union k is equal to 1 to infinity R power k. But what is this? This is just RT star. So what we have shown is that RT star sub T composition with itself is in fact less than or equal to RT star, which implies RT star is indeed T-transitive. Now this is the first part. We need to prove also that it is the smallest such transitive relation containing R. So we need to prove So to this end, let us consider an S which is T-transitive plus R is less than or equal to S. We need to show that RT star in fact is smaller than S. This is what we need to show. So that means it is smaller than any other T-transitive relation containing R. Now, R is less than or equal to S implies, look at R2. What is R2? It is R circle T R. But we know by the monotonicity of this composition that this is actually smaller than S circle S. But since S is T-transitive, we know that this is less than or equal to S. That means from here we get R2 is in fact less than or equal to S. Now, what happens to R3? R3 is nothing but R circle R2, but R is less than or equal to S, and R2 is less than or equal to S. So this is less than or equal to S circle TS, but which is again less than S because S is T-transitive. So this implies once again that R3 is also less than or equal to S. Now if you go on like this, for any n, we see that R of n is in fact smaller than S. Not only for Rn, for every n this happens. That means, this implies, even if you take the union, this will lie below S. That means it is smaller than S. But what is this? It is nothing but RT star. So, as was to be proven, if there existed an a relation S which was T-transitive and contained R, we have shown that the T-transitive relation that we have come up with, RT star, is in fact smaller than S, which means it satisfies both the properties that is expected of transitive closure, and thus RT star is indeed the transitive closure of R. Now, we can come up with some interesting corollaries based on this result. As mentioned, it is not only a result, it is also an algorithm because it allows us to actually determine the transitive closure. Now it is clear that a relation is T-transitive if and only if it is equal to its transitive closure, because that's the smallest transitive relation containing it. And what is interesting is, one might wonder, how long should we go on? Because we have to find R, then R2, then take the union, again take the union with R3, so on and so forth. But interestingly, if R is a reflexive relation, and if X is finite, say it has only n elements, then it can be shown that RT star is in fact R power n minus 1. In fact, it depends on the values there. RT star can actually be much smaller than that. It's just that there will definitely exist a K less than or equal to n minus 1, such that RT star is in fact equal to R power K. So in the case of reflexive relations with a finite domain underneath, we see that this is a process which is not never ending and quickly converges, at most in finite steps. Okay. In the previous lecture, we have taken this set X consisting of these 7 elements, and we have looked at 2 different relations on them. On the left now, what you see is a similarity relation. It is reflexive, symmetric, and min-transitive. On the right, we have only a compatibility relation. We in fact showed that this is not min-transitive. For instance, if you look at the colored numbers, you can see that minimum of R of GE, which is 0.5, and minimum of R of GE and R of EF, which is 0.7, is in fact 0.5 and not less than or equal to 0.4, which is R of G gamma F. So we said that the relation on the right, R, is only a compatibility relation which is not min-transitive. It might interest you to know that the relation on the left, S, is in fact the transitive closure of R with respect to min, obtained by this very procedure that we have listed out. Well, now for some practical illustrations, I would like to show you through some simple MATLAB code how you could visualize this. Well, let's look at some examples now. Consider the same relation that we have discussed in the previous lecture. Now you will see this is the compatibility relation that we have taken now. Now let's look at how to generate the corresponding similarity compatibility classes. So we have 7 elements, A, B, C, D, E, F, G. That's how we have listed them yesterday. However, on the plane here, we have 7 points. These are the coordinates of these 7 points. And now, if you consider for the alpha at 0.4, we know that all of them, the indicator matrix consists of 1s everywhere, and hence there is exactly one compatibility class. All of these 7 elements fall in it. So as you can see, the number of compatibility classes is actually equal to 1. Now, let's take this next alpha cut. In this case, alpha is equal to 0.5. Now we see that this is exactly the indicator matrix that we have got, the alpha cut of the relation R, which is only a compatibility relation. We have seen yesterday, it does not have a pure block submatrix structure. However, in this case, first we have a block here. A and B are related to each other, and that is what gives rise to the first compatibility class, as pointed out by these 2 elements here. Next, we saw that these 3, that is C, D, and E, they form a compatibility class. So here we see that these are the 3. Now finally, we have seen at this level of alpha, that alpha is equal to 0.5, we see that there is an overlapping block here. That means this compatibility class consists of D, E, F, and G. Already D belongs to another compatibility class. It also belongs to this compatibility class of D, E, F, and G. And now that is what is indicated here. You see that this element is related both to the magenta class and also to the green comparability class. And so is the case with this, because we had earlier C, D, E, and now D, E and E, both of them belong to 2 different compatibility classes. So as was mentioned yesterday, these compatibility classes do not form a partition. In fact, they overlap. Of course, they form a cover. Now let's look at a different resolution. So at alpha is equal to 0.5, we have 3 compatibility classes. Now this is the alpha cut for alpha is equal to 0.7, I guess. Once again, you will see that these 2 elements are actually staying together now. Now you see that again here you have C, D, and E staying together. However, now things get little different. Now you will see that these 3, that is D, E, and F, they actually form a compatibility class. D, E, and F. So you see in D and E here, they belong to 2 different compatibility classes. And finally, you also see that D, E, and G, they in fact are related under this compatibility relation. And in the 4th compatibility class, what you see is both D and E belong. So now you see these 2 elements, they have 3 circles around them at this level. That means they in fact belong to 3 compatibility classes. Let's go one level further up. We see here that A and B stick together. Once again, C, D, E, they stick together. And now, if we go further like this, we see that we have 4 compatibility classes, but now D and E belong only to 2 of them, not to the 3 of them as it did earlier. Finally, this is at alpha level 1. We see that we have these 2, these 3. This is 1 separately, and this is 1 separately. Of course, when alpha is equal to 1, what we get is a classical equivalence relation. So we actually get a partition here. So now look at the similarity relation that is given here. is exactly the similarity relation that we have here, which is obtained as a min-transitive closure of this particular compatibility relation. Let us do the same thing as we did before. Now you see here, once again you have the 7 points. They are arbitrarily generated on this plane, and at the level of alpha is equal to 0.5, we know that all of them are related to each other, and so you have a single similarity class. But now if you take the alpha at the level of 0.7, we see that we have a nice block matrix structure. A and B are related to themselves and nobody else, and C, D, E, F and G are related to each other and not to A or B. So that's how you see the first similarity class consists of these 2 points, which are A and B, and the other similarity class consists of the rest of the 5 points. Now, 2 similarity classes as indicated here. If you move up to the resolution level of alpha is equal to 0.8, we see that still the block structure is maintained. A and B are related to each other. C, D, E and F, they form a similarity class, and G separates out. So these are A and B for us. This is the second similarity class, and this is the final one, which is a singleton. Now at the level of 1, we still have some block structure here. At the next level, there are 4 similarity classes, and finally when alpha is equal to 1, we see that because of this block structure here, we see that C and D are related to each other. They stay together under the same similarity class, and rest of them become singleton similarity classes. Now, allow me to stay with this a little more. In here, what we have are 20 points arbitrarily created, and we have some kind of a similarity relation generated on these 20 points. Now let's look at what happens when we start looking at alpha pairs at different alphas. Now this is the smallest alpha, so all of them belong to the same similarity class. At alpha is equal to 2, and there are 2 classes. So this is a slightly different color than what you see here. So this fellow stays separately, whereas rest all of them belong to the same similarity class. Now the moment you increase the alpha, then we see that there are 8 similarity classes. Now a caveat, please don't go into this grouping or clustering based on visual distances between these objects. Instead, think of them as nodes on a graph, and each of those edges is weighted with the similarity value. Now what this algorithm has done, because of transitivity that is embedded in the relation, we are able to see that these points, they are actually related to each other. Even though if you go with the distance, they are not, but based on the similarity relation that we have extracted or unearthed in whatever scenario, it could be a set of people. Each of these nodes could be a set of people. It could be somebody who is giving his preference on a set of attributes, and that's how we have generated the similarity relation. Or it could be each one of these nodes could be a portrait, and the similarities between other portraits is what has given us the similarity relation. And now we are trying to group them, in some sense cluster them. So now you see here, even though they are physically apart, but they seem to be having the same likeness in terms of the attributes they prefer, or in terms of the resemblances in terms of in their photographs. Now, if we go like this, we see that slowly at different resolutions, as you increase the alpha, increase the threshold of acceptance to be similar, we see that we are getting a finer and finer groupings. It means we get more groupings, and obviously we get less number of people or less number of objects in each of those groups. So this is one way of doing clustering. It also goes under the name of relational clustering. These are some illustrations which have shown you that if you take a compatibility relation then you get overlapping compatibility classes. While if you have similarity relation, that means if you take a compatibility relation, apply the transitive closure, make it min-transitive, and get a similarity relation, then by taking different alpha cuts at different resolutions, you are in fact able to get a partition on the underlying set, which effectively turns out to be groups or groupings on the set of objects that you are considering. A quick recap of what we have seen so far. I said we have looked at fuzzy relations, and in that we have looked at two different special types of binary fuzzy relations, that of similarity and compatibility. Note that transitivity plays a role here. When we discuss composition of fuzzy relations, we did not see them in terms of transitivity, but we now know that transitivity is related to composition and composition is related to transitivity. Finally, when we are discussing similarity and compatibility classes, we have seen the key role played by transitivity there again. And in today's lecture, we have seen how to infuse transitivity to a fuzzy relation if it doesn't have one to begin with. In all these things, transitivity has played a role. What next? In the next lecture, we would like to see how the transitivity of a fuzzy relation is related to the triangle inequality that you can get from a metric, or in the language of kernels, the positive semi-definiteness of a kernel. And you see that in that sense, fuzzy relations can also be thought of as kernels or as being obtained from metrics themselves. In fact, if you have a similarity relation, as was already mentioned, similarity and distance, they can be thought of as dual of one another. And this is what we would like to deal with in the next lecture. The algorithm that we have seen here and some of the related properties are very well dealt with in this book by Clear and Boimon. So this can form a good source if you want to read up on the topics that we have discussed in this lecture. This is the paper of Tamura and others, published in 1971. In fact, in the very first issue of a volume of IEEE transactions on systems man and cybernetic, wherein they deal with a collection of photographs of members of some families, and they try to actually group them into families based on relational clustering. Finally, what we have seen as relational clustering based on similarity relations on set X can also be thought of as hierarchical clustering, a particular form of hierarchical clustering. And if you would like to know more about this, a good source on this topic would be the book by Miyamoto and others titled Algorithms for Fuzzy Clustering. Glad that you could join us in this lecture. Hope to meet you soon in the next one too. Thank you.